We were supposed to do this maybe about a year ago, and then, well, as with everything, COVID happened and things kind of got rescheduled. So I'm really excited that I'm giving the talk now, because what I was going to talk about then is trying to see how we can use XAS to tell us something about mechanisms during catalysis. And the students have been incredible, actually, over this entire period. And this last year, we sort of really put the pedal to the metal and figured out some really interesting things that I hope to share with you today. So, so good morning to everyone, and thanks for coming. And as Jerry mentioned, I'm at UCSD now, and our research group sort of has really three research focus, I would say, but they're sort of broken up into these four different sort of themes. We're really interested in sort of what happens at material interfaces, complex interfaces that might comprise, say, a solid and a liquid, or two solids. And in terms of the solid liquid, we're usually quite interested in the solid liquid interfaces as they pertains to battery materials or some kind of electrochemical device. And so what we're showing here is some previous work we had done where we use XAS to sort of map out what's happening at the electric double layer, these alternating layers, supposedly alternating layers that form in order to neutralize a surface charge. And in particular, we were looking here at the sort of prototypical electric double layer that one might form, which is in a sort of sulfates and sulfuric acid on platinum, which is kind of a textbook electrochemical interface. And using XAS, actually, we were able to point out that the typical picture that people generally think about in terms of you sort of charge this platinum interface. And if you look in your textbooks, at least I had to go back and check this, but most of the textbooks would say that over a certain voltage, you start forming platinum oxide on the surface. And using the XAS, and in this case, a surface sensitive XAS that was developed at Berkeley by Miguel Salmeron, we're able to show actually that at those potentials, you don't form platinum oxide. Rather, what you have is you sort of just have these sulfate anions that sort of fuzzy-sorb at the surface. And how were we able to do that? Well, that is basically the focus of this talk and the power of XAS in chemical mapping that we can get. So on the left, we have our theory predictions for these structures, and on the right is the experiment, and we get a pretty good match there. We've been generally interested in energy storage materials, and so if we go from the interface and start looking at the bulk, we've been really interested in what happens to lithium and other ions as they start coordinating in the bulk, and what the spectral signatures from that coordination is. And in this case, in project number 2, we're really interested in lithium sulfur batteries, and trying to use XAS to tell you something about speciation in lithium sulfur batteries as a function of applied voltage. Recently, we've become really interested in this field of resonant catalysis as it pertains to both water splitting, but also generally speaking as it pertains to different reduction reactions, the CO2 reduction reaction, and we'll talk a little bit about that today. But the general idea, which was sort of laid out maybe about 10 years ago, is that if you have certain small molecules that can bind to a catalytic surface, there is some sort of frequency at which these molecules are vibrating. And so that if you can somehow match that frequency, you can catalyze these reactions and overcome this Fatfier principle by switching the surface in some intelligent ways. And so we'll show you some of our recent efforts at looking at using XAS to actually probe the small molecules and and actually gives us spectral signatures that we can then interpret to follow the reaction. And in project number 4, we've sort of gone beyond all of these linear absorption techniques, and we're now really interested in nonlinear X-ray spectroscopy, and in particular combining different types of spectroscopies, some frequency generation, second harmonic generation, with soft X-rays to sort of develop unique probes that can tell us something about what's happening at material interfaces. And in particular, buried interfaces that can actually also be charged. And we've had some really good success recently in looking at solid-solid interfaces as it pertains to solid-state batteries. But as I said today, we're going to primarily focus on catalysis. So project number 3, and we'll give you 2 examples of using XAS to tell us something about the mechanisms that underlie catalysis. Okay, so this is not necessary for this crowd, but I just thought it's worth mentioning that we can have a variety of different processes that arise from the absorption of X-rays by a material. And in particular, we can have sort of ionization events where we absorb X-ray photon, and that then ejects, that causes the core electrons that are resonant with the incoming photon to sort of get ejected. And so this is XPS. Of course, we can also have, instead of it getting ejected out into the medium, that these core electrons get absorbed. Rather, they transition into unoccupied states, and this is the principle behind X-ray absorption spectroscopy. One interesting part of this, of course, is also what happens to these excited states after these initial either sort of ionization or absorption events. And here we like to think about 2 sort of events that can occur. One is a non-radiative Auger process where we have valence electrons sort of that falls down into the core hole that's generated by absorption of the X-ray photon, and then that causes another valence electron to sort of get ejected. And so this is the process behind Auger spectroscopy. Or we can have X-ray emission spectroscopy, where this valence electron quenches this core hole, and we get a photon coming off that we can then detect. So this then provides us with a whole suite of tools that we can use in order to probe the electronic states of materials, and really powerful set of tools that can tell us something about either the excited states, the core states, or even the valence and conduction band states that results that are in these materials. And what is particularly exciting is that not only are these types of spectroscopies inherently sensitive to the element itself, sort of how deep that core electron is lying, but they're also very sensitive because that we start probing either the valence or the conduction band states as well. They're also very sensitive to the local environment, so that we can start getting information not only about the element and the elemental specificity, but some sort of information about the local environment that this atom is sitting in. And so, so this is all pretty powerful, and we have now a global XAS forum that we talk about this all the time and about how awesome this is. Of course, all of this happens at a variety of different light sources all over the world. In California, on the west coast of the US in particular, we have quite a few facilities that do this. And because I did a postdoc at Berkeley, I'm sort of obliged to trumpet the ALS, the Advanced Light Source. And also, I was at the Molecular Foundry, and in there, you can do electron loss spectroscopy EELs at the National Center of Electron Microscopy. And so effectively using an electron microscope to give you spectroscopic signal. We've done some work previously, and I'll show in a moment, using X-ray Raman spectroscopy that one can do at SLAC in Stanford to look at bulk materials and the properties that are there. But whichever light source that you use, sort of the underlying principles are pretty much the same. And this idea, this excitations from core states to, in the case of X-ray absorption, to unoccupied states then becomes a really powerful tool for material science. So we've been really interested for a long time now, ever since my sort of end of my PhD, to try to understand the different processes that one can model on a computer, the different X-ray absorption spectroscopies that one can model on a computer. And there are a variety of techniques, and towards the end of the talk, I will talk about some advances, at least some more sophisticated ways of dealing with this. But probably one of the more efficient ways of dealing with this is within density functional theory and the application of Fermi's golden rule within density functional theory in order to model the X-ray absorption process. And so if we walk through it a little bit, we have that the X-ray cross-section area for a particular incoming frequency is equal to some transitions from initial states and final states with this delta function, of course, which then governs whether or not we actually get a spectral signature, right? So that if the difference between the final and initial state matches this incoming X-ray photon, then we get these transitions then become strong and allowed. And so that means if we have some good way of modeling the initial and final states and the transitions between them, we can start getting reasonable approximations to the actual X-ray absorption process. So again, we can do this within density functional theory. And here, the general idea is that this initial state would be the ground state of the system, and the final state would be some core excited state. Practically speaking, what that means is that we run two density functional theory calculations. One is just our usual solving for the electron density of the system in the ground state. And the other one, we create a core hole and we place it at a specific atom center. And then we rederive the electron density for that system in the presence of that core hole. And then the final piece of the puzzle, of course, is to calculate the overlap matrix between our initial and final state. And we can make in this approach that is commonly used, we can make this approximation that this formally many-body wave function can be approximated by the single electron sort of wave function here, where we this should be I at this point here, where we simply use a scaling factor, uniform scaling factor, to approximate these single electron excitations. And so, at this point, you're kind of like, hey, wait a minute. DFT to do this, DFT is a ground state theory, should not work for a core excited state. How does any of this work? How does any of this make sense? And it turns out that a lot of the issues with using DFT in particular is since it's a mean field theory, is that the electrons effectively see themselves and the self-interaction error. That more or less goes away when we start looking at these core holes and these excited states that are generated from the core holes, because we get sort of these core holes are so deep that we get extreme localization of these excited states around that core hole. And so all of these subtle effects that we get within DFT, at least traditionally, that has been an issue using DFT in calculating things like UV vis or visible spectra, pretty much goes away, and we're able to get pretty accurate sort of spectroscopy using DFT within sort of this approach. So it's there are various different ways of treating these final states. We can we adopt the approach of Prendergast at Berkeley, where the final state is the excited electron is placed in the lowest unoccupied molecular orbital, or in the conduction, the smallest conduction band state, and this is the so-called excited electron and core hole approximation. So we've used this now over the years to look at a variety of things. I'll skip the previous slide and I'll come back to it. But I just wanted to show this example of using this approach to actually do a very simple crystalline. In this case, this is lithium fluoride. We were interested in this because lithium fluoride and sort of different lithium salts turns out to be significant components of a variety of solid electrolyte interfaces that form on the cathode and anode of batteries during charging and discharge, initial charging and discharge. And so there is for a long time now, there's been a push to try to understand the composition of these solid electrolyte interfaces and to maybe try to engineer new ones that will be more effective and more mechanically stable. And so it turns out that XAS is a very good probe at looking at these sort of compounds, because we get distinct spectral shifts depending on the coordination environment around the lithium. And so if lithium is next to fluorine, we sort of get this black spectrum here. So we take a lithium fluoride crystal and put it in our XAS machine. We get this black experiment here. The dashed line shows the sort of the lithium white line that we expect. So this is the first major transition that we expect for lithium, right around 63 eV, 62.5 eV or thereabout for this material. But what's really interesting in the experiment is that we actually have a low energy peak that's right around 61 eV or thereabout. It's a little shoulder here. And so for a long time, there's been a question as to whether or not this shoulder is real or not, or is this some sort of radiation damage, or does this just come about because we have some sort of impurities, other sort of impurities in the system. But this is pretty reproducible. You can take lithium fluoride compound and put it in, and you get this more times than you don't. So then we thought, well, this might be quite interesting to check out as a first test to see whether or not this approach is sort of admittedly sort of simple. We're making all these approximations within DFT, whether or not this is able to capture the physics. And so the important thing to note here is that if we actually just take the experimental crystal structure at 0 Kelvin and we calculate the spectral response, the XAS response, using at lithium and K edge, using that structure, we get this blue peak, that this blue spectrum that's shown here. So we're able to get this first peak, and it looks okay. I would say, in my very scientific way, we sort of start getting these general features. It's a little bit more spiky than the experiment, more well defined, but generally everything is pretty much in the right place. But we are missing this very first peak, this low energy peak that is below the first transition. And so, but what's really interesting is if we do a molecular dynamics simulation, or we can sort of sample using other techniques. But if we sample the structure at finite temperature, and so the MD that we ran in particular is shown to the right here, and you sort of see this motion that is happening, and the lithium is moving a lot more than the fluorine at 298 K. And if we take these structures, the snapshots along the way, and average over all of them, we actually get this red curve here, and indeed we start getting this pre-edge feature that shows up here. So it seems at least that this pre-edge peak in the experiment may be real, but then the question is, what is the nature of it? So why do we actually see it when we get the MD structure as average, but not the crystal? And the answer is, well, that there's actually a dark state here. It's sort of, but it's symmetry forbidden because we're within this dipole approximation. And so you usually cannot get transitions from sort of lithium 1s states to S-like orbitals because of it violates sort of the selection rules. But what happens during the MD is that actually this S state sort of starts hybridizing with some of the P states that are on the fluorine. And so they gain a little bit of what we call P character. They're no longer a symmetric state. And because of this asymmetry, the overlap now between the lithium 1s orbital and this sort of new hybrid sort of SP state gets some amount of overlap, and then this dark state effectively lights up. And so we get a spectral signature that comes from this hybridization. So this was particularly interesting. We showed this about 10 years ago, that this happens not just in lithium fluoride, but in a whole bunch of other lithium compounds, lithium nitride, lithium oxide, and so forth. Some of the times we see the dark state because they're sort of at low energies enough that they're actually you can actually resolve them, and other times they're there, but they're sort of close enough to the main transition that they're actually hidden. You do see in a lot of these compounds a change in slope right at the low energy, right at that first transition. That is the signature of them, but it's usually really difficult to resolve that experimentally. But by and large, for this, any kind of rock salt structure that we've done with lithium, we actually see this dark state, and it's predicted that its intensity should grow as the system gets hotter, as we heat it up even more. So, so we've also then we figured, well, all right, it works for lithium salts. Maybe we can start looking at some more interesting system. And this system was particularly interesting for us because we were interested in lithium in these lithium sulfur batteries, which are, have incredible promise, but have been for a long time now have been held back by the fact that during cycling, we get these short chain lithium sulfur species that are soluble typically in our electrolyte. And so our sort of cathode material starts degrading over time. And so we only typically able to get a few cycles out of this battery before it dies, which is not great for commercialization process properties, because it matters little if you can have a battery and that can drive you from LA to, or at least to be more apropos, from Seattle to New York on one charge. That's great, but if you have to take that battery out and replace it every 5 trips that you do, that's probably not going to fly as a commercial product. And if lithium sulfur batteries are able to realize their full potential, these energy, a trip like from Seattle to New York on a single charge might actually be possible. So so there's a lot of excitement for these batteries, of course, but then the question is, how do you actually prevent this sort of degradation of your cathode? And one idea was to, well, maybe we can just encapsulate it into these nanospheres, these carbon nanospheres. Then by kind of mechanical sort of encapsulation, we can keep them within these nanospheres and keep them from flowing out. And so this is a lot of work that has been pioneered over the years by folks like Linda Nazar at University of Waterloo and Yi Shui at Stanford, showing that you can make these sort of nanoscale confinement membranes, effectively, that can allow you to cycle lithium sulfur batteries quite a bit. I think, as Jerry mentioned, my PhD was in sort of thermodynamics of interfacial systems and nanoscale systems in particular. And so looking at this, I thought, this is a completely crazy idea. I mean, in particular, I was convinced that once you start loading up these structures, these nanospheres, that the sulfur actually is going to go into the pores, and they're not actually going to go into the center of this thing. So what you really want is all of the sulfur in the center of this nanoshells, and then so that you can do the chemistry and reaction in the center. But I was pretty sure that they actually went into the pores, and you can start seeing it if you do these sort of these high resolution dark field imaging, that you can start seeing these sort of illuminations right in there at the edges here, and not much contrast in the center. And so as you start loading, and so if you go from low loading to high loading, indeed it starts filling up the center. But if you have a habit of low loading, you start seeing it on the outer shells. And so the reason for this has to do with sort of the interfacial thermodynamics of the system, but more importantly, we can actually use XAS to think about what's happening to the sulfur molecules that are in the system and the local environment. So the idea being that if they're in the pores, they're going to form these sort of kind of nanoscale sort of pore networks, whereas if they're in the middle, they look much more like bulk sulfur. And so by using 2 systems where we had sulfur in a nanotube versus sulfur bulk sulfur, we're able to show that you get about a 0.3 eV shift in the XAS. And true to form, if you actually take these experiments and take these low loading versus the high loading, you actually see about a 0.3 eV shift in the XAS. So the XAS is very, very sensitive then to the local sulfur environment, such that what's really happening in this system is that, and this is primarily shown in figures A and D here, is that if you sort of have sulfurs right next to carbon, because of the sort of the electrostatic screening that we get from these graphitic layers where we have these electron clouds here, they tend to affect the 1s energy levels on the sulfur. And so that's where effectively these 0.3 eV shifts come by. We do get changes in the very first conduction band states depending on the amount of screening. But the important thing is that the screening of the 1s core states is significantly more than the unoccupied states. And so overall, we get a 0.3 eV shift here. So we're able to show basically not only, and this primarily happens because these sulfur states, and we'll see a little bit more of that in a moment, these core excited states are really localized around the individual sulfur molecule. They're not hybridized with anything else. So this was some work that we did maybe about 5 years ago, now showing that not only do you get these sort of molecular states for sulfur, but that these molecular states are very, very sensitive to the local carbon environment. And then that can then be at least a local environment, whether it's carbon or sulfur. And then that difference can be probed with XAS and give you about a 0.3 eV shift, which you can see in experiments at the sulfur K edge, which have resolution of about 0.1 eV these days. All right, so this might be a natural place to stop and take some questions if there are any so far.
Excellent. We'll start. Micah, you have a question?
Yeah. So this is great stuff. I was wondering on your lithium fluoride slide, you had the static calculation.
Yep.
Which got most of the features, but they're a little too sharp. But that spectrum is broadened by some like broadening parameter, I assume, or I guess that's my question.
Yeah. Right. So I think Micah's question is related to this sort of well-known effect in DFT to sort of underestimate band gaps, depending on the functional, but certainly at the level of theory that we're doing here, it's known to underestimate band gaps and concomitantly also underestimate sort of the width of the unoccupied spectrum, basically. So this is a well-known, and so the answer to your question, Micah, is yes, there is, I believe, we apply a dilation to all of these spectra of about 5%, if I remember correctly. There are other ways, there are better ways of doing that, more sophisticated theories, better, if you use better functionals, it turns out. You can sort of mitigate a lot of these effects, but you know, these additional better physics obviously come with a price. And so for this particular work, we applied sort of an empirical broadening depending on the material.
Yeah, well, I mean, I think most of the broadening comes from the thermal motion, right? And so I guess
I'm sorry. I just meant a dilation of the spectra because of this issue with the band gap. Yeah. But yeah, most of the broadening here, in terms of these peaks being not as spiky, comes about because of the thermal motion. You're correct.
Yeah, and that's a theoretical prediction of the MD, I guess. That's the point I was making.
Thank you. Great question.
All right. We've got some questions going around on the chat related to the S-type character of this pre-edge feature for the lithium. My first question is, do you know if it's exotonic? Because there's a fair amount of literature about that question, at least at the fluorine K edge. And there's been X-ray Raman scattering there that shows that that pre-edge feature is definitely S-type at the fluorine K edge.
Yeah. It's an interesting question. In terms of the exotonic nature of that peak, we did not look at that. I am aware of the literature at the fluorine K, sort of related to that. Not so much at the lithium K. I imagine that there probably is a significant amount of exotonic character to it, but we did not look into that.
I see. Okay. One more question. If you go to your sulfur slide with the sulfur near the carbon, yeah, and the energy shift and all that, what's the mole fraction expected to be for the sulfur that actually is close enough to the carbon to have these shifts?
Yeah, so it's about, so we do it in terms of the weight percent of sulfur that's in our, so 30 weight percent sulfur basically gives this, fills the pores. And that just has to do with sort of, on average, sort of, you know, the size of your pores and how much actual space, because the pores fill first. It's sort of the bottom line that we figured out. The pores fill first, and then once the pores are filled, then we start getting filling of the internal. So this 30 weight percent would represent enough sulfur to fill all of the pores in this case.
Sure, but not all of it is interfacial. Maybe I'm
not all of it
is
interfacial. That is true.
That's the mole fraction I was curious about, and whether this can be observed, or if there's so many sulfurs that are not interfacial that you can't see this energy shift experimentally.
Yeah, it's a great question. So for this particular sample, the average pore size here was about maybe a nanometer to a nanometer and a half. So these were really, really small pores for these carbon nanoshells.
Okay.
And so most of those would be actually interfacial sulfurs, which is why you're able to get the signal. Yeah.
Perfect. Now I understand. All right. Seeing no more questions, pardon me, you should continue.
Okay, so we can continue. All right. So one really interesting new thing that towards the end of my postdoc that we sort of started working on is sort of how to make XAS very, very surface sensitive. So the previous work, the XAS was surface sensitive because these pores were a certain size and there was effectively mostly sulfurs next to carbon. But as a general principle, how do you do this? And so this is some work by Miguel Salmeron, where they came up with this cell that can be used to probe solid liquid interfaces in particular. And so walking you through it, you have this silicon nitride sort of layer at the back end, which is transparent to X-rays. And you have your working electrode, and this can be gold or any other metal that you want to use. Here, could be lithium, I imagine. And you then sort of start illuminating the cell. So this is some liquid that is in here, in the center here. And then what happens, of course, is that this X-ray goes in, and then you sort of get all kinds of X-ray processes depending on the incoming energy. We're particularly interested in the oxygen K edge, and for a aqueous system here, looking at salts in water. And so the lithium comes, so the X-rays come in, do these excitations. And then you get a fluorescent signal, of course, our usual fluorescent signal that is bulk sensitive. But then you also get these OJ electrons that sort of result from the X-ray absorption process, as I mentioned at the beginning of the talk. And these OJ electrons sort of have a relatively low mean free path. Now, we've been trying recently to figure out exactly what the mean free path is, but just it's widely accepted in the literature that it's probably about a nanometer to 1 to 2 nanometers. And so these, so what this means is that these OJ electrons, the only ones that are going to reach our current collector here, which is our working electrode, are going to be the ones that are within the molecules that are within about a nanometer of the electrode or so. And then you can then effectively take the current that comes out of your current collector here, chop it up with a chopper, and resolve the resulting X-ray absorption spectra from that. So this was the experiment. Turns out to be a really neat experiment. And so if you do this for, again, just any cell in water as a function of voltage that you apply to your working electrode, you get, well, before you even get the voltage, so this is an open circuit potential. If you then look at the signatures that you get, you see that for in the case of our TFY, so our bulk measurements, we get our curve A that shows the characteristic XAS of water, showing 3 peaks, one at 535 eV, that's the signature typically of broken hydrogen bonds. So if you have hydrogen bonds that are broken in this system, then you get a peak at about 535 eV, and then you get sort of this main peak here that is about 537 eV or thereabouts. And then this peak at higher intensities, about 541 eV, that's also supposedly a signature of hydrogen bonding. So this is the usual peak in A that you get for water. So this is a good confirmation. We're not doing anything too weird in our system. The water in the middle of the cell looks like bulk water. Also, if you do this in the total electron yield mode, so this way that you're sort of harvesting these OG electrons and then resolving the resulting current, you get, if you have a hydrophobic layer on top of your gold, in C here, you pretty much reproduce the bulk water spectrum pretty exactly. So it looks like the water molecules next to this hydrophobic layer that's on top of the gold, and this is, I believe, C18 chains or thereabouts. So not very large, but large enough that these things are probably more than pretty far away from our electrode. Then you don't see any real difference. But what's really interesting is if you look at the peak in B, which is the total electron yield just on the gold itself, that this peak A here, this low energy peak that I told you is related to hydrogen bonding, disappears. And so the interpretation of this was that, well, maybe on gold, we have a situation where you have perfect saturation of the hydrogen bonding, and that really only happens in ice. And so the prescription was that on gold, we have an ice-like overlayer. We have a water overlayer that's ice-like next to the gold. So yeah, anyway, so we can, we've been looking at XAS of water, of course, for a long time. This is the low energy peak that I told you that's related to this 535. This is 4A1 peak. And you can see sort of at here, we have electron density that in this core excited state that sort of is lying along the hydrogens. So the hydrogen sort of right outside of the hydrogens, we sort of get the electron density for these states. And it turns out that you can actually use XAS. This was shown quite a few years ago, that you can use this delta SCF, this DFT approach, to get the XAS of ice and water in pretty good agreement with the theory, or with the experiments rather. And in particular, in ice, we get the absence of this 535 peak, and in regular water, where we have about 3.5 hydrogen bonds, so a broken hydrogen bond in every 2 water molecules, then we do get this pre-edge peak here at 535 eV. So that's all pretty well established. And so then the question is, if we actually take a simulation now of gold with water on top of it, do we actually see an ice layer? The short answer is no. We actually see this sort of layering that you get from sort of having a broken symmetry in the system, where you sort of, so this happens anytime you have water next to the interface, hydrophobic or not. But then what's really interesting is, from our simulations, we can actually take the first nanometer of water molecules that are on our simulation and then calculate their spectral response. And what we find is that we do this, and we get the peak that's shown in B here, the spectrum that's shown in B, very much in good agreement with the experiment. But this is not ice. This is, in fact, very, very disordered water molecules. And just for a sanity check, we can do the same thing next to this hydrophobic interface, and we get the spectrum that's shown in C here. And so this seems like it's all working out, but the interpretation of the experiment, the initial interpretations of the experiment, turned out to be faulty. And what we found, at least doing the calculations, was that we have a whole bunch of different water molecules that can be on the surface. They can be having hydrogens pointing towards the gold or away from the gold, or lying flat. And we were able to analyze just sort of the populations of these different species at the interface, and then calculate the spectral response of each of these different types of species, right? So double donors, saturated hydrogen bondings, so single donors with broken hydrogen bondings that can either be parallel or perpendicular. And by looking at this, we find effectively that at in the bulk, we have sort of about 20% have broken hydrogen bonds. That's consistent with what we see before. But at the AU interface, we actually have significantly more broken hydrogen bonds, and so we get a population of water molecules that are pointing into the gold, in particular. And those I don't have the plot here, but those gold atoms, those water molecules that are pointing into the gold, don't have any density here, even though the hydrogen bond is broken. What happens is that 4A1 state sort of hybridizes with the electronic structure of the metal. It becomes completely delocalized now. So it's no longer a molecular state, it becomes sort of a delocalized state. And because of that, the overlap with the 1s, the oxygen 1s, is very low, and so that this very first peak disappears. And so the signature that they were seeing experimentally was not of ice, but of actually hybridization of this core excited state, the very first core excited state with the metal band structure. So I point this out only to show that by using theory and at least using this DFT approach, we're able to start uncovering some really interesting physics, and specifically interesting physics that may happen in sort of interfacial systems that might be kind of surprising. Okay, so that is all sort of old work. Let's move on to some new work that we've been doing. And Jerry's smiling because I'm sure I'm almost done with time. But let's talk a little bit about catalysis here. And in particular, we've been really interested in CO2, the CO2 reduction reaction on various catalysts. There's some really good ones. People have been really excited about these transition metal dichalcogenides, these MOS2 and molybdenum diselenide, molybdenum disulfide. And here we can sort of just have a cartoon of the different intermediates that may form, where we can go from sort of CO2 in the air absorbed onto here and some sort of reaction that then leads to different products that you can get. And so we're really interested in trying to use XAS to potentially follow this reaction, but also follow this reaction electrochemically. So what happens if we start charging and we create nanoscale molybdenum disulfide features, and we start charging it? Can we understand which species actually are stable as a function of charge? And so that was the motivation here. We have some work from our experimental colleagues at University of Chicago at Illinois, University of Illinois at Chicago, rather, where they sort of looked at both the molybdenum K and the sulfur K edge, and then track the XAS as a function of applied potential. So they have the dry cell in this case, and then they start flowing on it, at the sulfur K edge in particular, start flowing CO2 over it. And then they also have a electrode set up where they can change the potential, the applied bias. And so what you see here is sort of the evolution, as it were, of the sulfur K edge, going from black, which is the top, the dry cell, all the way down to applied voltage. What we see is this very first peak, the sulfur white line, peak at 2472, decreases in intensity, and then we get an increase in intensity of this the second feature here. And in addition, there's another feature that sort of decreases in intensity as we do the applied voltage. So the question is, what is the spectra that we're seeing? What is the molecular origin? Or are we seeing different chemistries here? Or is there just some sort of screening event that is happening that is causing the core excited states to actually change in nature and in their character? So to do this, then we started having to develop an operando version of the XAS that we've been looking at before. And here we chose to employ this effective screening medium approach of Otani, so that in the ground state, we can actually perturb the ground state as a function of applied bias, and then also get the resulting XAS spectrum that sees this new potential that the system is experiencing. So as a function, so as we start adding effectively if you wanted to do a finite voltage within computationally, usually what you would do is try to modulate the electron density that is sitting in the system, right? So the charge and the voltage are conjugate pairs. And so if you change one, you change the other, in other words. And so by trying to control the electron density at the surface, then we have a way of controlling the applied voltage. And so this is done self-consistently within DFT, within this effective screening medium approach by Otani, which is shown here effectively. And so we applied this effective screening medium within our DFT XAS to have effectively an operando XAS approach that we can then use to follow the actual progression of our XAS as a function of applied voltage. And when we do that, what we find basically is that applied voltage is not enough. That even if you start cranking up the voltage, you're not going to really see the different changes in the experiment that were observed in terms of the modulation of this first and second peak. What you really needed actually was to sort of have sulfur vacancies in the system. So if you had sulfur vacancies that then reacted with the CO2, then you get this peak right at the bottom here. And it's a little messy, but basically we have the dry cell from the experiment in red, and then the high cathodic bias, so the experimental result for the high voltage that is in orange, so red and orange, and you can see the difference between the red and the orange in terms of the peaks here, this first and second peak. And so then we can also do our calculations now of the defect-free system, which is shown in purple, if you can follow all of these crazy curves here. But also, if we start then binding CO2 and then doing this at applied voltage, we get sort of the green peak here. And by some wizardry by my really talented grad student Saswat, we're able to effectively track by looking at the peak areas between this first and second peak. We are able to track that sort of the XAS. The experiment is shown in blue and red and solid lines, so the different peak ratios. And we get a very similar peak ratio computationally if and only if we assume that the mechanism involved in results from generation of sulfur vacancies at low bias, and then electrochemical reduction of the CO2 that are bound to the sulfur vacancies at higher potentials. So, the idea here is to have candidate structures at every single potential that we then simulated their spectral signature and choosing the pathway that was consistent with the experiment. And by doing that approach computationally, we were able to show that the only way you would get the experimental spectra that was shown is if you actually had this mechanism that is what has been postulated for a long time, but this now is direct spectroscopic evidence that this is the only mechanism that is at least consistent with the experimental results. Okay, so I'm almost done, but maybe this is a good place to stop as well.
Let's hold the questions for the end.
For the end, okay, brilliant.
Okay.
All right. So this is tracking the active states of CO2 reduction by this electrocatalysis. Another thing that we've been really interested in is this idea of ferroelectric switching of a surface. And so the general idea is that we have sort of a catalytic surface, and that catalytic surface, if we can modulate the surface morphology, by modulating the surface morphology, we can cause different molecules to bind with different binding energies effectively. And so if we can target, if we know for a specific surface that we have, if we can then target the rate limiting step and switch the surface such that the binding energy at the rate limiting step is reduced significantly, that means that we can accelerate the reaction resonantly, right? So the way that we came up with switching the surface was using a ferroelectric material, in this case, barium titanate, and then exposing it to some sort of electric field at a specific incoming frequency. that will then cause this ferroelectric material to either be pulled up, where sort of the titanium atoms move upwards, or pulled down, where they sort of move downwards. And so you're modulating the surface that way by using an incoming electric field. And more importantly, we've shown computationally anyway, that these pulled up and pulled down surfaces have different binding affinities. And in this case, for the CO radical, and so, which is a rate limiting step in some of these CO2 reduction reactions. And so the real big goal here was that, you overcome this sort of the Sabatier principle, which says that, you need a binding that's in this Goldilocks zone, not too strong and not too weak. And so you need a material that is going to sort of just bind these intermediates in sort of this Goldilocks. And of course, probably the best one would be platinum. But here we're basically showing by selectively changing the surface, at least resonantly changing the surface, you can use other materials, and in this case, barium titanate, and get sort of reaction, conversion reactions that are comparable and competitive with platinum. So that's a general idea. So my other really talented grad student, Pedram, who does both experiments and theory, sort of did these measurements up at Argonne. And so they have their sort of STXDM, so you can do scanner-tunneling microscopy for imaging, as well as do XAS at the same time. So you can get both spectroscopy and chemical mapping at the same time. And so that allows you to zoom in on specific parts of your sample and actually get both sort of structural and electronic information from it. And so the system that we're really excited about is this sort of system of NS-steel with barium titanate on top of it. So we have our ferroelectric that is sitting on top of our usual catalyst. And so we have a thin film of ferroelectric material whose surface we can change, but it's thin enough that it actually doesn't screen too much the catalyst that is sitting on below it. And what's really interesting is that Pedram, using this approach, was able to do a whole bunch of different measurements at the barium M, the titanium L, and the oxygen K edges for the different pulled up and pulled down surfaces, and basically show that you actually get a specific spectroscopic signature for these different surfaces that he was generating resonantly in this case. And in particular, for the pulled up, where again, the titanium moves towards the surface and distorts the octahedron, we get spectral signatures with more intensity than in the pull down cases. And we were able to reproduce all of these spectra except the barium M edge, but certainly the titanium L edge and the oxygen K edge using the beta salpeter calculation specifically for the L edges, where our DFT approach fails spectacularly. But we're able to sort of get really good agreements with the T2G and the EG peaks, both for the L3 and the L2 features at the titanium L edge using this beta salpeter approach, and an overall good agreement at the oxygen K edge. But more importantly, we were able to show that consistent with the experiment, we do get enhanced intensities for the pulled up surfaces versus the pulled down. And so, combining this then with our DFT calculation showing that we get modulation in the binding of these intermediates, now opens up the door for us to potentially use this resonant catalysis approach to start engineering new interfaces and new surfaces that can selectively bind different intermediates and overall accelerate our CO2 reduction reaction. So that is to come. We have some really exciting work showing that this actually works, but I'm way over time, so I'll stop here. The students who did all of this, Saswat did the first bit looking at CO2 reduction reaction on MOS2, and Pedram again did all of the work looking at resonant catalysis. This is my email, this is funding and our collaborators. I'll take any questions that you may have.
Very fun stuff. Thank you. Yang Ha, you had a question?
Yeah, it's been very interesting, but I'm just curious in your molybdenum sulfide studies, since you collected the sulfur KH, usually we would just move like 100 EV above and we get free molybdenum LH signal for free, which will give you some electronic information to the system, like the maybe CO back into the molybdenum. I don't know, any comments on that?
You were breaking up towards the end there, but I think the question was, why didn't we just do this at the molybdenum LH? Because if the CO2 is binding to the molybdenum, then the spectral signature probably would be stronger at the molybdenum LH. And the answer to that is a great question.
Right. So you mentioned
this is the experiments. We do have molybdenum LH experiments that have been collected. For reasons that may be apparent, the DFT approach is pretty bad at doing LH spectroscopy in general. So this delta SCF approach that we've been using so far is really bad at that. And we have a way of doing it now within sort of a more sophisticated theory, but then that introduces some computational challenges that means that looking at a system like this is not computationally feasible. So we do have experimental LH. We just don't have a computationally feasible way of actually getting for this system for getting the computational results. But yeah, you're correct. You're perfectly right. Looking at the LH of the molybdenum, it's quite clear that there is significant modulation at the molybdenum LH, and so probing the physics there is something we're working on.
Thanks.
Okay, I'll ask a question. If you can go back to the, I think it was the next to last slide with the pull up, pull down results.
Yep.
So I guess what I'm trying to understand is there much change in spectral shape in the experiment between the two, or is it just an overall amplitude scaling factor?
So these are the experiments that have not been scaled, right? So these are just coming out of the beamline on B and C are the two experiments, and D and E are the calculations. And so there isn't much change in the line shape, it seems. It's really just the intensities that are being modulated.
It's just doing, sorry, I've got someone with the hoist behind me. It's just, are there any concerns about systematic effects? Because I mean, getting absolute cross sections in XAS is pretty tough, and I understand the experimental configuration didn't change, or at least we hope it didn't change. But any concerns about a possible experimental artifact that would give an overall scale factor?
Yeah. But if you look at the T2G and EG peaks, for instance, for the L3 and the L2, they are being modulated by different amounts. It's not just a uniform modeling of the features. So, and we've sort of, we've done like the paraelectric phase effectively of this material.
Okay, that makes a lot more sense.
That it's all within expectations in that the paraelectric phase lies in between these two extremes in terms of spectral intensity.
All right, last question from John Vincent.
Oh, sorry. I was wondering if you think ESM is good enough for your needs in terms of calculating X-ray spectra of systems that have some applied potential.
Yeah.
Or is there a need for more development?
Yeah, it's a great question. So John's question is, so when we're looking at this operando XAS, we sort of use this ESM approach basically to give us a new external potential, or a new potential that the system is seeing, and then we're solving effectively the DFT within that new potential. The question is should we be doing more? Is that reasonable? Well, the answer is then, yeah, we should be doing more. There are more sophisticated ways of doing it, and we've been investigating those. ESM turns out to be a good compromise between a reasonable physics and as well as computational tractability. We have more sophisticated ways of doing it. It's just that it turns out that they're not particularly useful for a lot of the material systems that we tend to look at. I hope that answers it, John.
You good, John?
Yeah, thanks.
Okay. All right, we're at the hour, and so let's all thank Tod. It was a terrific talk, great mix of experiment and theory across a number of really interesting systems. So thank you for taking the time to give the seminar.
Thanks, folks.
With that, I'll
Much
stop the
appreciated.
recording.